Okay, it's 4 p.m. So let's just start first. So uh, today we'll be doing rotation, and we'll basically cover this from the perspectives of rotational kinematics and rotational dynamics, broadly speaking. And there'll also be a short section teaching you about moment of inertia and how to calculate it. So essentially, you can treat this chapter as like a rotational version of whatever you have learned in kinematics and dynamics. There will also be some oscillations in here. So it will require everything that you know from before that. So without further ado, let's just get into it. So for today, our subject of focus is how things rotate, right? So why do we even need to know about this? Well, if you have tried in real life, if you have tried like opening a door or like pulling or pushing it, if you know that to exert the least amount of force possible, you need to push the door at, suppose this is the pivot, you need to push the door here at the end to minimize your force that you need. And of course, this is important because your door is not a point mass. So it has some length and clearly it is not of negligible size. So that's what we're trying to do in this chapter lah, to analyze objects with that are like actually massive and have size instead of treating everything as a point mass like we did in the previous few chapters. So first we will go into the kinematics of this. So as usual, we don't care about where rotation comes about. We just want to analyze quantities, and the quantities that we're interested are, in this case, theta, omega, and alpha. And the names for these are the angular displacement, velocity, and acceleration, respectively. So uh, you also have your time as usual because time is always there. And there's a nice way of thinking about this in terms of analogy because your x, which is your linear displacement, is directly analogous to your theta, which is your angular displacement. Likewise goes for your v and your omega and your a and your alpha. So what this means is that you can essentially just treat rotation as another version of translation, which is very nice because all the quantities are in some way analogous to each other. And it's not just the kinematic quantities. Later on, you see that there are a lot of other quantities that can be directly mapped to the translational quantities. But you, but from this, you have the relations here. These are definitions, and you can see that this directly comes from mapping it to this and mapping it to this. So, yeah, these are definitions. These are useful when you have varying time varying. For example, if you have a time varying omega and a time varying alpha, you can do stuff with that. You can integrate to find your theta and your omega respectively. Likewise, as you have seen in kinematics, you have Suvat equations in kinematics. So here you also have rotational Suvat equations given by these. These, of course, assume a constant alpha, which is your angular acceleration. So these are quite self-explanatory. It's just about how you apply the equations. So I'll go into the more like in detailed part. So the first thing we want to look at is rolling. So rolling is what we call a combination of translation and rotation. So when you see an object that's rolling, the object is both translating and rotating at the same time. So for instance, this purple ball here, you can see that it's rolling forward. So it's moving forward. It's moving forward on the table. And you can see here that its center of mass here has some speed of VCM. And the whole ball itself is also rotating about the center. So you can see that the center is translating and your ball is rotating about the center. And this gives rise to rolling. So here we see that rolling can always be broken down into translation and rotation. This will be quite useful when you want to analyze how the velocity vectors and everything interact with each other. So here we see that there are two main types of rolling that we are always concerned about. The first one is rolling without slipping. Second one is rolling with slipping. So rolling without slipping is the very nice case because you can always write this when an object is not slipping. So usually in problems, usually most of the time you will want to assume this. Most of the time. Keyword being most, because some of the time you can't assume this. If a problem doesn't state whether something is rolling with or without slipping, it is usually assumed to be without slipping unless that assumption gives something that is really weird or like nonsensical. So you usually assume that it is without slipping, if not stated. But any good problem will state whether it is slipping or not slipping. So when it's not slipping, you can relate the center of mass velocity to the angular velocity of the whole object. So in this case here of the ball, you can see that your VCM and your VCM and your omega are related if this ball is not slipping. But there's also a not very nice case if the ball is slipping. If it's slipping, you cannot write this. Oh, there should be a R here. Yeah, so you cannot write this if it's slipping. And how we actually get equation 7 is because when something is rolling without slipping, basically your normal formula for your arc length is this, where S is your arc length and theta is the angle that spans it. And if you just differentiate this with respect to time, then you end up with this. And the reason why you can even write this is because if it is not slipping, then your object, so like let's say if your object moves like that, say we have a blue portion here. So if your object is moving this way, then if it's not slipping, you can see that after a while it will become like that. And it has simply just traveled the same blue portion here. So yeah, you can imagine it as like the amount of blue portion that the object has moved through will be equivalent to the amount of distance that it moves on the ground. And that's why it's not slipping. And that's why you can write that relation there. So these are the two types of rolling that you should know. And again, if you differentiate this with respect to time, you will get this. And so this just means that there are a lot of ways to express the non-slip condition. So you might be thinking, if there's rolling with slipping, you cannot write this, then you essentially lose one equation, right? Because you are not able to write VCM equals to R omega. So you lose one equation here. But you actually get compensated you get compensated one equation, because when something is slipping, so when something is slipping, friction is kinetic. And you know that for kinetic friction, you can write this. Whereas for static friction, you can only write this. So notice that there's an inequality sign here compared to an equality sign. So actually, this is your compensation when something is slipping. You can write this equation when something is slipping. But when something is not slipping, then it has static friction between between the surfaces in contact. And you can only write inequality here. So in a sense, even though you lose the non-slip condition, you gain the kinetic friction equation. So everything will still be well defined, and you still have enough equations to solve any problem that concerns slipping. So one caution is that when there's no slipping, friction is static, and because of this, it doesn't do any work. But if there's slipping, friction is kinetic, so friction will do work. So you need to be very careful when you apply energy conservation when you're dealing with slipping. Basically, you need to account for the work done by friction. Okay, so that's for slipping and not slipping. The next concept about rotation is the instantaneous center of rotation, which we'll call the I-core for short from now on. So if we go back to the diagram here, so you see that there's some random point on the ball called P2 here. And basically, because the ball's motion can be comprised of translation plus rotation, each of this will contribute some velocity, which we will call V trans and V rod respectively. Which means that the net velocity, the ball at of the point 2, will be the sum of the translational plus rotational velocities. Because each of these contributes one component of velocity. So the easier case to see is the translational case, because your CM is moving at VCM, and your CM is not rotate. Your CM is the point that's not rotating about the CM, because a point cannot rotate about itself. So your translational speed at this point would just be VCM, which means that you can think about all the points on the ball. They are translating with VCM in the direction where the CM is headed, and that is their translational component of their velocity. So this is the less complicated part. The more complicated part is about the rotational part. For the rotational part, this is actually given by omega cross R, where R is given by this vector. So your sign conventions for omega, just to recap, if your omega is going this way, then you can use your right hand and right hand grip rule. You grip your direction of your fingers in the direction of omega, and your thumb will tell the direction of omega. So in this case, omega will go into the page. So it's this direction. So you can see that by doing this, and then you can apply your right hand rule on omega cross R. You can see that the rotational velocity will point in this direction as expected. So what this means is that the velocity at any point can just be expressed as VCM plus omega cross R, where R is the position vector of the point with respect to the CM. And this is a very important relationship. This holds for any single point on the ball. So two interesting points that we always like to look at will be the top of the ball, P1, and the bottom of the ball, P dot. So if you look at the bottom of the ball, which is P naught, then your V net will just be VCM plus omega across R naught. Your R naught points like that. Your R1 points like that. So assuming this ball is not slipping, then so assume non-slip, then you can write VCM equals to R omega, right? If you evaluate this here, you will get that this is just VCM minus VCM. And this will be 0, which implies that P naught is stationary. So what does this mean? P naught is not moving instantaneously. And that's why we usually call this point the I-core. So in this case, P naught is the I-core of this object. So you can see here, I've done exactly this. At point P naught, VCM and omega across R naught perfectly cancel out. So VP naught is 0. So why is the I-core useful? So this is useful because it gives another way for you to visualize rotation. So to visualize rolling, sorry. So rolling can actually be viewed as a fixed axis rotation about the I-core. So instead of what I said just now, where we view the rolling as the translation of the CM and the rotation about the CM, you can now see rolling as having an axis through here. So imagine an axis through this point, and the whole ball rotates only about this fixed axis. You can see here that it produces the same result as if you just treated the rolling as what I mentioned earlier. So an equivalent definition is using the I-core. Fixed axis rotation about I-core. And yeah, this will also give you rolling. So yeah, the I-core is quite powerful. Another nice geometrical fact that you can use that confers the I-core is that any point on the rigid body moves perpendicular to a line drawn to the I-core. So an example is shown here. If you draw, so let's say you draw a line connecting point P2 and the I-core, which is P naught. Then you draw the velocity V2, which if you recall is the vector sum of the translational and rotational velocities. This simply states that this makes a right angle. This is a right angle. And we'll skip the proof, but you can try proving it as an exercise. So this is just a nice geometrical fact that you might use sometimes when you do rolling problems. Okay. So we will now look at how to deal with rolling. So one common thing that is used in rolling problems are spools. So spools are basically a yo-yo. You have a few cylinders and you have a string that's wrapped around them, and then your string is just being unwound. So in this case, you have an inextensible string that's around this cylinder. It has an inner radius of r, small r, and you have an outer radius of big R. And your string is at a fixed angle theta with the vertical. Now you want to find the cm speed of the cylinder if this is being pulled with speed small v. And you're given the assumption that it rolls without slipping. So the best way to approach this problem is define your quantities first. So of course, you define big V as the cm speed of a cylinder. And because you're given that it rolls without slipping, you can write this condition. So up to now, this should be quite straightforward. So now the perhaps not so straightforward part is how do you proceed from here? And there can be quite some confusion because there are two radii, so you might not know which one to use. And the easiest way that I would recommend thinking about this is to think about a specific point on the body that is being constrained. In this case, the most convenient point to think about is this point in blue. The reason is because this point is connected directly to the string, and the string is always being pulled at a speed of small v. This means that the velocity of this point is being constrained to fit this string constraint because the string is inextensible. So the velocity of this point is forced to be small v in this certain direction. And what we want to do right now is to turn our perspective to this point basically. So here, we can draw all the relevant velocity vectors on this diagram here. And yeah, this point here is A. So if the cm speed of the cylinder is big V here, then clearly it's moving this way, right? The cylinder is moving this way, which means that it is rotating this way for it to move this way. And you can write the rotational velocity caused by the rotation at this point A, and is given by this vector here, which is omega small r. So now that you have this, you can simply just write the constraint relation for the velocity at point A. And you have a vector of omega small r here. Then you have a vector of big V here. And this means that you have a vector of big V sine theta here, which means that you have a vector of big V sine theta here. And these will sum up to small v here. And this is what this equation is. And that is how you get your other equation that you need by fixing the velocity of some point on the body. So now this is a matter of rearrangement and using omega, and you eventually get this. So the lesson to learn from this example is that you can take a convenient point, some velocity vectors at that point, and then constrain the velocity of that point. So constraints are usually found in the form of, in this case, strings, and sometimes you can see inextensible rods or other objects out there. The point is that if you have some point that is being constrained, then use it to your advantage in solving problems. So that's what this shows you. Now we can look at another example here on how we apply this equation, which is very important. So now you have a wheel that's rolling without slipping, right? And you have many spokes on this bicycle wheel. So the wheel kind of looks like that. Okay, yeah, pardon my bad drawing. So the wheel kind of looks like that. You have many spokes along here. So you take a picture of this wheel and you realize that most of the spokes look blurred except along a curve or special points. So you want to find what this curve is, right? So the main insight is that if your points are not blurred, right, you want your points to be moving parallel to the spokes. So for instance, if I say that this specific blue point is not blurred, then at the instant where I take my picture, this point should be moving in this direction, which is parallel to the spoke that it lies in. Now the reason for this is because your camera takes a small time to capture the picture. It's a very short time. But you want to ensure that in this small time, when the picture is captured, this point still lies along the spoke. And if it does, it will still appear to be clear. And that's the rationale why you want to consider the points that have the velocity vector that's parallel to the spoke. So we start again from this basic equation. So if you have, so let's say you have a random point here. This has a position vector of small r from the CM, which is the center of the wheel. Then you have this, which is what I've explained earlier. If you want the velocity to point along the spoke, then your velocity points this way, right? Which means that V is parallel to R for it to point along the spoke. So now that we have the intuition down, we can set up a coordinate system regarding this wheel and all the spokes that we have with it. So let's say the wheel has a radius of big R, and we set up coordinates like that so that the I core is at the origin. Recall that the I core is just this point here because the wheel is not slipping. The I core is at the origin. The center of the wheel will then be at 0, big R. And we can consider the velocity of some random point, which we call x0, y0 on the curve. So we can draw a picture here. The vectors will look like that. And you can see here that if we draw a line from this point to the I core, it will be perpendicular. If you draw, it will be perpendicular to the velocity vector of this point. That's the nice geometrical fact that I used from just now. So we can describe the gradient between this point and the I core. It's just simply this. And from equation 11, which is this, the nice geometrical fact, you can see that because of this, the velocity vector is perpendicular to this gradient. And so the gradient of the normal line will be -1 over y0 over x0, which is just this. So we can then find the equation of this normal line, which is just this line here. And by using the fact that it also passes through x0, y0, you can write this and you can rearrange to get the equation here. And now once you have this, you need to plug in a set of points that you need to plug in a y and x that this line passes through. And from this diagram here, you can see that the most convenient y and x you can plug in will be x, y, because it's 0, r. And plugging that in, you will get this. And you can see that's exactly what I did here. So now a bit of rearrangement, you actually get to this form of equation, which is simply describing the equation of a circle with radius. This is your radius of big R over 2, and it's being centered at 0, R over 2. In other words, your special curve actually looks like that. So if this is your wheel, your special curve actually looks like that along the wheel. This is the curve of points that do not appear blurred. So from these two examples, there are a lot of lessons you can learn. Firstly, in using constraint equations. Secondly, in how to use the I core to your advantage. And yeah, I think it's quite important to revisit these two examples to understand the importance of considering all these vectors and considering the I core. So yeah, vectors are kind of underrated. Okay. Are there any questions at this point? Okay. If not, then we'll just go on. So next we have moment of inertia. So I talked about analogies between rotation and translation just now. So this is also another analogy. The rotational analog of mass is just the MOI, or the moment of inertia. So we can just write something like this. Moment of inertia is usually denoted as I. And it depends on the geometry of the shape because it influences the mass distribution. For instance, clearly the mass distribution of a point mass from a given axis is different from the point distribution of a sphere, even if the distances of the point mass and the radius of the sphere are the same. Clearly, the mass distribution is different, and they will have a different moment of inertia. So always remember that moment of inertia is calculated about an axis. So sometimes you might see certain books or certain notes say that we are calculating MOI about a point. That is partially true because they are considering a situation in 2D. And in 2D, an axis can reduce to a point in that perspective. But you should always know that when we consider MOI, it will be always about an axis. So here are some common MOIs that you should know because these objects are quite common geometries. I would highly recommend you to memorize a few more common ones, which I will take right now. Yeah, I highly recommend you to memorize these more common ones because these objects are just so common that you don't want to spend too much time deriving the MOIs on spot. And sometimes in less well set questions, they don't give you the MOI and you're just expected to either memorize them or derive them if you don't know them. So memorizing these will save you a lot of time. But this is not a memory contest, so let's see how we can actually derive them. So yeah, you're highly encouraged to memorize them, and you realize that you actually just need to memorize the numerical prefactors. For instance, memorizing things like half, 1/12, 2/3, you don't really have to memorize that much, per se. Okay, so if you're interested, there's also a whole section on the appendix. I've linked like 4 research papers there, and you can look at how the many different methods of calculating MOI are. But these methods are just for fun, so you usually don't need them. Okay, so we first define what the MOI is. If you have a lot of point masses, the MOI is defined as this: the sum of MR square. And consequently, the MOI of a point mass is just MR squared. But again, this only holds for a collection of point masses. It doesn't hold for it technically holds for it technically holds for continuous mass distributions, but in this case, it is much more convenient to just use integration. So as an integral, you can express MOI as such, where your R is the distance of the mass dm from the axis of interest. Okay, so let's look at how we can use this integral. So here we have a uniform thin disk of mass m and radius r about its central axis. So it will look like that. And your axis is into this page and out of this page. So the easiest way to calculate MOI for this case is to just integrate. And there's a clear symmetry because this is just made out of many, many, many concentric rings. Which means that we can first solve the problem, a sub-problem. What is the MOI of a ring about its central axis? So you can see here, that's what we did. We found the MOI of a ring about the central axis through integration, and we just want it to be MR squared. Because the nice thing is that for a ring, all the mass is equidistant from the axis. And we can just take out the R square from the integral. That's why we have a nice result. So that's for the ring. So now we turn our attention back to the disk. We can define the mass density per unit area of the disk as such. So just M over A. This is like density but for area. And you can then integrate over all the rings of the all the rings on the disk, which means just integrating over all the infinitesimal di's, and you can eventually get half mr squared, which is consistent with what is described. Okay, it's not described here, but it's consistent with what you should get. So there's another more involved example with a uniform solid sphere of mass m and radius r about its diameter. But essentially, this goes back to the same steps. And if you want to find MOI, you should always just go back to these two steps. First, find the density. So this can be either a linear density, area density, or volume density. Second, slice your object into many infinitesimal objects. And you want symmetry as much as possible. Now, once you do this, the third step is to find dm, which is equals to your density times your infinitesimal volume, or your area density times your infinitesimal area, or your linear density times your infinitesimal length. And then once you have this, you can integrate r squared dm to find moment of inertia. So just follow this framework here if you ever need to find MOI. This is like the key framework that you can use, and it's quite convenient to do so. If you get more comfortable with it, you probably don't need to go through the density step. But yeah, if you're just starting out, then I would highly recommend you to think in terms of density first. Okay, so you see here that in this case, we slice the sphere into many disks and we follow the same framework. We can find the volume of each small disk as such, and we can integrate over all the disks to get 2/5 mr squared, which is consistent with the earlier image. Okay. Now, we go into the parallel axis theorem, which is a way we can simplify MY calculations. So this theorem is simple. It just states this. And you have basically 2 points here. Some random point of interest. And you have axis through the CM. Then you have a D here. This D is the distance between your point of interest and your axis through the CM. Point of interest and axis through CM. So yeah, that's it to the parallel axis theorem. Now the hard part is how to apply this. So it's a very common mistake when you apply the parallel axis theorem to write an equation like this. I2 equals I1 plus MD squared, where you just took any random points 1 and 2. Now this is wrong. When you apply the parallel axis theorem, your point 1 here must be the CM. So you can't just write a relation like that for any 2 random points. It just doesn't work. So there's a small subtlety here that you need to be careful with. So example 1.5 is quite trivial. It's very simple application of the parallel axis theorem. Now a more complicated application would be example 1.6, where we are given the MOI of a uniform equilateral triangle. So you know this, you're given it about an axis through one of its sides and parallel to that side. So this is the axis. You know that I equals to 1/8 MA squared. So you're given this. Now they want you to use this result and calculate the MOI of a uniform regular hexagon about an axis through 2 opposite vertices. So here we'll see how to use this result using the parallel axis theorem. So first we draw the hexagon. It looks like this, and the axis looks like that. And you can see here that at this point we can label different triangles because we want to split it into triangles for us to use our result. So you can see here that we labeled 4 with A and 2 with B. Now the reason is because the 4 triangles with A will contribute the same amount of MOI, and the 2 triangles with B will contribute the same amount of MOI. And it's just purely due to symmetry because they are the same triangle. They are the same type of triangle with respect to the axis. So we label the triangles as such. So now what do we do about this now? Each triangle has a mass of m/6, where m is your hexagon mass. Each triangle has a side length of A. So we can see that for the A triangles, we can directly use this result, and we can plug in into this. So the A triangles each contribute 1/48 MA squared to the total MOI of the hexagon about the axis. So the A triangle is easy. But the B triangle is a bit hard because the axis is here and the triangle looks like that. So how do we find the MOI like that if we only know this? How do we find this? So this is where you use the parallel axis theorem, because you're given this. So you have the CM here, which, by the way, for an equilateral triangle, you should know some geometry to it. The geometry is stated here. So this is the CM. We apply the parallel axis theorem twice and see that the first time we can find the moment of inertia through the CM by applying it in reverse. So we take I, the given I from the result, minus the distance, minus m times the distance to the CM squared, and we'll get this through the CM. And then we apply it again to get it through the axis that we want, and we will get this. So each B triangle contributes this MOI. Now we can find the final MOI by just summing 4IA plus 2IB, and you get 5/24 MA squared. So the hard part about this problem is actually applying the parallel axis theorem twice. The first application here, so this one might be a bit difficult to spot, because instead of finding I about some other axis using the ICM, you're doing the reverse. You're finding ICM using the I about some other axis. So this is sometimes used as a trick, and you should be able to know how to spot it. So applying in reverse is quite a sneaky trick that you should know. Now, from this example, you can also show that if you're not convinced that this doesn't work, you can try using this. You can try going from here directly to here, and you can see that your result will be different. So it doesn't work. Which means that if you just instantly did something like if you just did something like say like that, yeah, this doesn't work. So always go through your CM first. Your CM must always be there. Okay, so that's for the parallel axis theorem. For another theorem we have is the perpendicular axis theorem. So this actually only holds for planar objects, or we sometimes call it pancake objects, which means they are objects in 2D only. You can write this relation for these objects, relating the MY through the z-axis and the MY through the x and y axis. So the most common application for this usually only comes when you have symmetrical situations where your Ix equals to Iy, and that's the bulk of the time where you use this. So example 1.7 is quite a trivial example that shows you how to use this. This is perhaps less common than the parallel axis theorem. So yeah, but just know that this exists and it's useful for planar objects. So now that we understand kinematics, we can now go into dynamics. So in dynamics, we'll deal with quantities such as torque, angular momentum, and other stuff later on. So for torque, this is how we define torque. R cross F. If you have something here, like a coordinate system, you have a point here with a position position vector of R, and you apply a force F at this point, then your torque is just this. Your torque will be calculated about an axis passing through here, the origin. So these are just definitions. Angular momentum is defined as R cross P, where P is your linear momentum. Again, this is a definition. So you can see that actually using this and this. Now, if you recall this relationship, you see that this just gives you torque goes to dl dt. And these are actually just analogs of each other. Now, so this can be another way of defining torque and angular momentum. Torque is just the time derivative of angular momentum. And because torque is the time derivative of angular momentum, you can see that if your torque is 0, then your angular momentum is constant with time. And this is what we call the conservation of angular momentum, or COAM for short. Which means when there's no net torque, angular momentum is conserved. We will see how to apply the COM later on. For now, let's look at the rotational analog of Newton's second law, which we call the Euler's rotation equation. So, for this part, if you have a fixed axis rotation, which means that your axis of rotation is fixed, then you can expand out the angular momentum like that. So here we just plug in d equals to mv, and we just expand. We use this thing called the vector triple product, which is technically out of syllabus, but it's just to show you the derivation. And you can see that you get mr squared omega, which is I omega. So L equals to I omega. It's another way of defining your angular momentum. If you just put this into equation 18, which is this, you will get this. Torque equals to I alpha. This is a super important equation. And this is your Euler's rotation equation. You can see how this is similar to Newton's second law directly. Torque is your rotational analog of force. Moment of inertia is your rotational analog of mass. Angular acceleration is your rotational analog of linear acceleration. So it's completely analogous, and that is how you can remember it if it is useful for you to remember it this way. Now there's this small subtlety here. If you apply equation 21 here, you need to consider the same pivot or axis for calculating your torque and your MOI. You cannot calculate your torque and MOI about different pivots or different axes, then your equation won't make sense in that case. So usually how to apply this is, don't forget your N2L exists. Your N2L will be used to write equations involving forces. Then you use equation 21 to write an equation involving torques, and then you solve the equations. My general recommendation is for you to write N2L first, so that you don't forget about it. Because you might be too excited to jump to the torque, and then you forget the N2L exists. Okay, so let's look at an example here from the SPhO TST, which is the SPhO team selection test from 2022. So you have a yo-yo made out of two uniform solid discs of radius r, each with mass m. So something like that. Connected by a axle. Oh wait, no. Connected by an axle of radius small r, and all of them share a common axis. So this is So now you have a string that's wound around here, and it's the free end of the string is held fixed, and the whole thing is released from rest. So first, you want to determine the downward acceleration of the yo-yo, and then you want to determine the tension in the string when the yo-yo is released from rest. The first thing you should do is to find the my of the setup. Now, because this is just two uniform disks, so it's just 2 times the my for this, and so it will just be mr squared in total. Now, like what I mentioned, you want to write N2L first. So I write N2L first. For the translational motion of the yo-yo, you see that if you draw like a side view diagram, it looks something like that. So this is your FBD. You can see that your 2mg minus t will be 2ma. So this is just N2L, nothing fancy about that. Now we go on to the torque. Now, if you write Euler's rotation equation about the center of the yo-yo, you can see that there's no torque by 2mg, because it's acting through that point itself. But there's a torque by tension. And the torque by tension is just T times small r, because it is small r away from the center. You set this equals to I alpha, you put in I here. And the last thing that you need is actually the non-slip condition, which allows you to relate A and alpha. So because your I core in this case is this point where the string is attached, you can see that because it's like that, your non-slip condition is actually A equals to small r times alpha. And it's not this. It's not big R times alpha. So this can be quite tricky for you to find out actually which radius do I use for my non-slip condition. So as usual, the easiest way to think about it is go back, constrain the velocity of this point, think about how the I core works, and yeah, that way you don't mess up the radius that you use. So this is the actual non-slip condition. So let's remove this. Okay. Now you have the equations here. 1, 2, and 3. You can solve them. You will eventually get this as your final answers. So yeah, so usually you want to do N2L, then Euler's rotation equation, then non-slip condition, then you can solve, and you get your final results. That is the framework, I would say. Okay. Now, a few more concepts here. We have rotational kinetic energy, work, and power. When an object rotates, there's a kinetic energy associated with rotation. Similarly, when an object translates, there's a kinetic energy associated with translation. So this is yet again an analogy. So your translational kinetic energy is given by half mv squared. So you know that your m is analogous with I. Your v is analogous with omega. So it should be quite natural for you to write this for your rotational kinetic energy. And indeed, this is the correct expression for it. So when you have an object that's rolling, you have to sum the translational and rotational kinetic energies. Now, recall that rolling is translation of Cm plus rotation about Cm, which means that your translational Ke is half m times your speed of the Cm squared, and your rotational Ke is half ICM omega squared. You sum them together to get the total Ke of your rolling object. So this is how you get your total Ke. I would really recommend you to always consider I and V of the Cm when you calculate total Ke. This will save you a lot of confusion on what V and what I for you to use. Basically, equation 23 will always work. So just use the Cm. Okay. If you have a rolling body, the instantaneous power by a force F, well, is just given by technically the translational power and the rotational power. So in translation, you know that this is your translational power. Now, your F is related to your torque, while your V is related to your omega, again by your analogy between rotation and translation. So it makes a lot of sense for you to just talk about your Cm dot your omega to just be your rotational power. And that is indeed correct. So when you have an object that's rotating, this is your associated power with rotation. And your work done will just, you can find it by just integrating this power with respect to time. And you get this. You get this here. So in equation 24 and 25, yes, the first term is translational work or power, and the second term is rotational work or power. Don't forget the rotational work or power when you're dealing with rotation in general. We also have the work energy theorem, which you probably remember from translation that is just this statement. So when you're dealing with rotation, if you want to, you can still write this, but you have to account for your change in rotational kinetic energy. So the main point is that literally everything in terms of work energy power, everything still holds from translation, except you have to introduce the rotational kinetic energy and then account for it in your kinetic energy, and everything will still hold. So it's quite elegant in that way. Yeah. Okay. So now let's look at an example where we consider the rotational kinetic energy. So here we have a fire hose, this whole thing of mass m and length L. And it is rode to a coil of radius r initially. So initially it's like that. Of radius big R initially. Okay. And we send this along level ground with the center of mass given a speed of V naught, which is much greater than square root GR. So this might be sending some alarm bells ringing, like, what is the point of writing V naught is much greater than square root GR? But okay, we'll look into what this means later. So now you have the free end of the hose here is held fixed, and the hose unrolls and becomes straight. You want to find how long this process takes to complete. Okay. So clearly there's some rolling involved, right? Because this part of the hose is rolling. So clearly you know that you need to do some rotational KE. And from there you have to do something with energy. So you might think about using energy for this. But first, let's rationalize what this means from just now. So you know that this implies this by just squaring both sides. And you know that if you multiply an m to both sides, this happens. Now, do both terms look familiar? I hope that both terms look familiar, because this sort of resembles kinetic energy, and this is literally just GPE. So what does this mean? Your kinetic energy is much, much, much greater than your GPE, which means that any changes in GPE are basically negligible compared to changes in kinetic energy. And this is reflected here. V naught is large, so changes in GPE are negligible compared to changes in KE. So when you write COE, you may drop all GPE terms, which is very convenient. This means that when you write your conservation of energy, all you need to consider is your changes in kinetic energy. So with that in mind, accounting for rotational kinetic energy, your COE equation is just like that. And if you put in all your terms correctly, you should get this, where your MOI about the CM is half mr squared for this hose, because you can essentially treat the hose as like a disk. Okay, so that's your COE equation. Now, you'll have also non-slip conditions, which give these. So it allows you to simplify the COE equation into this. Now, this is very nice. You can cancel the 3/4 and you can get V. You can get V in terms of big M, small m, and V naught. So now, small m is the one that's changing with time. Oh, by the way, the small m is referring to the mass here. The mass here that is rolling. So yeah, in case there's some confusion here. Okay, so this small m, the part of the host that's rolling, of course it changes over time, right? It will decrease over time. So what happens is that you can now express this small m using proportionality in terms of the distance that the host has traveled. If the host traveled a distance x, then you have a distance of L minus x left over. So proportionality will give you m times L minus x over L, which is just m1 minus x over L, to be your mass of the host rolling in terms of a function of x. Then, now that you have this, you can substitute that in here. And now you have a differential equation with x and t. Now you can separate variables and integrate. Integrating from x equals 0 to x equals to L, you get your time span will be 2L over 3V naught. Okay, so that's how you find the time. Now, some of you might wonder, why are we taking energy to be conserved? Why not we take any other quantity to be conserved? Why not like linear momentum or something? So the reason is, even though it might seem weird because the host is inelastically sticking to the floor, right? And when that happens, when you have an inelastic collision, you know that energy is not conserved. So it might be weird to say that energy is conserved for the host as it unrolls. Now, actually, this process dissipates no energy because the circular part of the host is rolling without slipping. So the bottom part is actually the I core. It has no velocity, so no work is done against friction. So this basically, this part is stationary. And there is static friction. And this combination will give you no work done against friction. And thus, energy is conserved. So that is why you can use energy for this problem. Simply because you have a non-slip condition and that point is your I core. Okay. So this was quite an involved example, but in most of the time when you use energy, just make sure that you account for rotational kinetic energy if there's rotation. Make sure that you write it in your COE equation. Yeah. Okay. Let's move on to more quantities. So now we'll analyze another type of dynamics where we have collisions. And a useful quantity that we look at is angular impulse. There's no standard way to write this, so we'll just call it J subscript theta in these notes. And again, this is the rotational analog of linear impulse. So yes, this is true. And it is defined like that. There also exists the angular impulse momentum theorem, which states that the angular impulse is the change in angular momentum. Very, very similar to the normal impulse momentum theorem, where you had this. Once again, this is an analogy, and this is a very useful analogy for you to remember this exists. Okay, so when you deal with rotational collisions, you usually deal with translation and rotation separately. You write separate equations for COM, COAM, and if it's elastic, you can write COE as well. So usually you have max 3 equations that you want to solve. And this example will show you how you do it. So here we have a rigid rod of length L joining 2 particles, each of mass m. Rod is on a frictionless table struck by a particle of mass m and velocity v naught. The collision is elastic and the particle moves straight back. You want to find the angular velocity after the collision. So first thing that you always want to do, find the MOI. Secondly, you want to look at the 3 different equations that I said just now. So first one is COM. This is your linear momentum. So in this case, you have m moving and v naught here. In your final system, you have, let's say your m moves back at v1, your rod here. Let's say your rod has a cm speed of v2, and let's say it has an angular. Okay, let's say it has cm speed of v2. Let's say it has an angular velocity about the cm of omega. So your COM equation is just like that. For your translational motion, we can cancel the m and becomes this. So this is quite easy to write. Now the next equation that's the next easiest to write is COE actually. So for COE, it's literally just dealing with a whole bunch of kinetic energies. Translational, and rotational. So don't miss this out. But provided that you remember not to miss this out, this also becomes quite easy to write because you're just dealing with the squares of the velocities. So there's not much to consider. Now, the possibly hard one to write is COAM. Because you might be wondering, COAM about what? So in this case, we will take the COAM about the axis parallel to V0 and passing through the initial CM of the rod, which is illustrated here. This is the axis we will take. And why we take this axis? Because if we take this axis and we consider our system to be everything in this picture, then there's no net torque about this axis because there's no external forces that act on this. No external torques that act on this system. Which means we can write COAM. And we can write this equation here. Now we need to be a bit careful with the signs here because of how the rotation works. And the easiest way for you to check the signs is just by doing just do the cross product using your right hand rule. And you can see how the signs are different. So just make sure that you account for the signs properly. For your right hand rule. So using COAM, you can get another equation. COE gives you this other equation, and as usual, now you have 3 equations in 3 unknowns, and you can solve for them. And eventually, you should get that omega equals to 4 root 2 over 7 V0 over L. So, few remarks here. For COAM, as I mentioned, be careful of the signs of each term. Determine the direction of the angular momentum vectors and make sure that you assign different signs to different directions. Another remark here is, why do we take COAM about this axis? Well, I answered it just now because there's no net external torque about this axis if we take our system as the moving particle and the rod plus 2 particles. But another person who solves this problem might have taken COAM about another point on our axis, such as an axis passing through the collision point parallel to V0. Now, actually, both of these approaches are equally valid. The only difference is what you consider as part of your system. Remember that if you want to apply COAM, the biggest condition that you must impose is net torque equals to 0 on the system. So as long as any system any point you choose, as long as you choose the system such that net torque equals to 0, that is valid for COAM. So for example, if you have chosen the axis to be about the collision point, if you instead chosen this to be your axis for COAM, then we should instead write our axis as only consisting of the rod and two particles. The reason being that is the axis, that is the system that will give net torque equals to 0. So yeah, you are free to take any axis you want. Just make sure that your system is defined consistently to allow for net torque equals to 0. Sometimes by taking a different axis, you might get simpler equations. So yeah, just keep that in mind. So again, to recap for rotational collisions, your key framework, okay, for rotational collisions, right? COM, COAM, COE for elastic, and then soft. For COM, be careful of axis plus system choice. And for COM and COE, they should be quite self-explanatory. So this is the framework that you should follow for solving rotational collision problems. Now we'll move on to another type of rotation, which is on physical pendulums. Now this kind of combines with oscillations. Because for oscillations, you learned that for simple pendulum, these are true. But the assumptions that you make here are that the pendulum bob is a point mass, the string is light, and so on and so forth. But this breaks down in real life because nowhere can you find a point mass bob and a completely light string, right? So instead, if you have a general rigid body that swings freely about some pivot point, you have made a physical pendulum. And the picture here shows a physical pendulum as well. So to analyze this, we can use the Euler's rotation equation on the torque due to gravity in this case. And you can write this. And if you are working under the small angle approximation, you have sine theta is approximately theta, and you can reduce this equation will reduce to this. Now, recall from oscillations that this takes on a similar form to SHM, where your omega square is just mgd over I pivot. So this indeed is also an SHM, but with a different period and different angular frequency compared to a simple pendulum. So the frequency and angular frequency and the period are shown here for a physical pendulum. And here take note that the moment of inertia is calculated about the pivot of the pendulum, not about the CM. So you can use the parallel axis theorem to help you simplify this calculation for the MY about the pivot. So here we have an example of a physical pendulum where there's a disk of radius r and mass md and a rod of mass mr and length l. You want to find the period of this pendulum first. So the period of this pendulum can be found just by applying can just apply this formula here to find it, which involves just finding the moment of inertia about the pivot, which is given as such, and then you can find the net torque due to gravity about this pivot due to the contributions from the rod and the disc, where this is L over 2. So you can find the net torque due to gravity, which is as such under small angle approximation, and we can then write Euler's rotation equation and simplify it to get the period for the SHM. So this is quite standard. Another way you can do this is by simply applying this formula, but it might be a bit more tedious because you need to calculate D, which means you need to calculate the position of the CM. of the system with respect to the pivot. So if you can do that, you can also apply this formula. It will also work. So now we have a part 2 here. In part 2, you're asked how the period changes if the disk is mounted to the rod by a frictionless bearing so that now it's free to spin. So previously it was not, which means that the whole thing moved as one rigid body, right? But now the disk is free to spin about its own axis. So what does this mean? It means that when you calculate MOI from this expression here, a certain term would die, and that term is this term. And the reason why it dies is because the disk is now free to rotate. It's not being constrained by the rod, and the disk effectively, for our purposes of calculating MOI, just basically acts as a point mass that goes about the pivot, which is why this term still survives. So that is the modification that we make to our MOI when we have a condition imposed such that the whole object is not one rigid body. So imposing this correction to the MOI, we can write the new period as such. So the remark here shows what's happening. When you add up MOIs, ensure that all the components we're adding up are rigidly connected, meaning that you can treat the whole body as one rigid body, which is why we had to throw away that term for part 2. So that's on physical pendulums and how you apply the equation. Okay. Before we move on to the ideas, I will check Discord again for questions. Oh, okay. I addressed it already. Okay. Okay, Ken. So let's move on to the ideas for rotation. So we have 3 ideas here. The first one is on massive pulleys. So we dealt a lot with pulleys in dynamics, right? Where we have like random systems with a lot of strings, a lot of masses, a lot of pulleys. And we usually just assume that the pulleys were massless and small. But clearly you can't find a massless and small pulley in real life, which is why we want to analyze what happens when we have a massive pulley. So when we consider rotation, pulleys are usually modeled as uniform disks of finite mass and radius. Consequently, the net force and torque on them need not be zero. Unlike here. Here the net force is 0. And because it's small, so torque doesn't really matter. But now net force is no longer required to be 0. So we can see an easy example here to show what it means. We have a pulley system with 2 masses, M1 and M2. M2 is less than M1. The mass of the pulley is big M and the radius is R. Assume that the pulley and string doesn't sit. You want to find the acceleration of the masses. As usual, we start with our free body diagram. So for the 2 masses, we have this. And for the pulley, now this is the subtle part. The pulley has a net torque, clearly, for it to rotate. Because the pulley has to go in one direction. And rotate in one direction to ensure that the whole system can move. For it to be a net torque, if you had assumed that the tension in the string is the same, then clearly there's no way it has a net torque, right? Because the torques would just cancel out. What this means is that the tensions actually are different. And you have to write T1 and T2 as such. So here, on the pulley, we also write T1 and T2 like that. And now we can proceed with writing our equations. So we write N2L first. And here, note that the A is the same. You can see A has to be the same because the length of the string is conserved. So that is what we call conservation of string. So A is the same. This is N2L. This is also N2L. And for the pulley, Euler's rotation equation will give uh give this, where this is just the net torque. So now you have three different equations. You can cancel R. The last equation is the non-slip equation, which directly just gives you this. So now you can see you have equation 1, equation 2, equation 3, equation 4. Four equations in four unknowns, which can be solved for T1, T2, A, and alpha. So you have set up four equations and four unknowns. Now you just need to solve them. You eventually get this as your A. Now, it is. Now you see that this kind of looks like a normal simple pulley, except you have this extra term here. So this is actually kind of like an effective mass that the pulley contributes to the total mass. You can think about it this way. So yeah, this is quite simple. So yeah, just remember that tension in the string is not constant to allow the pulley to rotate. So yeah, this is on massive pulleys. The second idea is about where normal force acts, because there's some confusion when it comes to rigid bodies of finite size. When you have, for instance, in this example, you have a cube of mass m, dimensions, all lengths are b, and is moving on this rough ground with coefficient of friction mu. Now you want to find the maximum external force that you can put at the edge such that the cube doesn't topple. So when you solve this, you just want to go back to the same stuff, right? You want to draw the free body diagram of the cube. And at first instinct, you might draw the free body diagram like that, where you have a friction, normal force, and you have mg. And your normal force acts at the center, at the base of the cube, and your friction acts at where your normal force acts, like that. And this could be your first intuition on how you draw the free body diagram. But you might see that there's alarm bells ringing here, because if you just consider torques about the center of the cube, let's say just consider torques here. Then okay, you have a force big F here, and you have a friction here. Your N and mg contribute no torque, but these two forces do. And these two forces contribute torque in the same direction. They cause your cube to rotate this way. So what does this imply? Would this not imply that regardless how small f is, the cube would topple? So this kind of implies that, right? Because your torque is always going in this direction. It's always going in the clockwise direction. And there's no counter torque in the anti-clockwise direction to stop it. So this is kind of weird. And well, the reason why it's weird is because this free body diagram is wrong. And the place where the normal force acts is actually wrong. So how do we draw it actually? So here we see that, so here we see the same thing. If we take torques about the CM, the forces mg and n contribute no torque, F and F contribute clockwise torque, and this will imply that big F can be as small as you want, which is clearly wrong. The correct way to draw the free body diagram is actually to shift the point of action for n. You can see here that the point of action is no longer such that n passes through the center of the cube. Now n is here and F is here. Now, why do we shift this? Because now that we shifted it, then you can see that n can actually give a torque now. If we take torques about the center of the cube, n gives a torque that rotates the cube counterclockwise, while small f and big F still both give a torque that rotate the cube clockwise. But now, because of the existence of this n, we can say that it is possible that the cube doesn't just topple instantly, no matter how small f is, because there exists some sort of counter torque to this. So drawing this correct free body diagram actually resolves the whole paradox. So now, with this correct free body diagram, assuming that your point of action of n is shifted by x, then of course by n2L you have these two equations. And if you take torques about the Cm, you have that you balance out your torque by n and your torque by big F and small f, you get this. And you can sub in n here, and you can sub in everything here, and you can simplify it to this. And this gives you the amount of shift that your normal force actually has with respect to the center. Now, there's one more constraint. Of course, you cannot shift your normal force such that your normal force goes outside of the block. So your other constraint would just be this, which is here. With that, you can successfully constrain your F to be less than or equal to mg times 1 over mu, which gives your maximum force in this case. And clearly, this maximum force is non-zero, which makes much more sense than having a maximum force of 0 in the previous case. So, what we can learn from this example is that if you assume wrongly that the position your normal force x in your free body diagram, then you get nonsensical results. In this case, 0, even the smallest force will lead to the cube toppling, which we know that is not true from daily life, right? So, if this ever happens to you, if we are dealing with rigid bodies, rethink where the normal force should act, because it might not be as simple as you think. It might not. Sometimes your instant intuition on drawing free body diagrams might not always be correct, and you should rethink where the normal force actually is. Now, the last part is on inextensibility constraints, which we are looking at rods here. When we deal with rods, you usually assume them to be inextensible or rigid, which means that you get another constraint equation by doing such a thing. So in this case, we have two uniform rods, each of mass m and length l, in a V shape. The angle of the V shape can vary, and the rods are released from rest when their angle theta to the horizontal is 45 degrees. We want to find the upward force that the horizontal surface exerts on the right rod just after release. The diagram looks like that. So the way to approach it is, as usual, you draw out all your forces, as I've labeled here, and you can see that there's a whole bunch of forces going on at this hinge area. So first thing my question is, okay, why is the Fy for the left rod upwards? Why is Fy for the right rod downwards? Now, this is just a guess, right? So if it turns out that we get negative Fy, then our guess was wrong, and we can just simply flip the direction of Fy. So the direction of Fy for each rod doesn't really matter here. Second thing you might ask is, what are these accelerations here doing? Okay, so these accelerations are what give rise to our constraint equations. The constraint here is that the length of the rods are fixed. And clearly the motion of the two rods will be symmetric, right? Clearly you will always, regardless of angle theta, it will always look like that, where your theta is the same. And this is not very hard to see. So to write our constraint equation, we can define this as our origin. Then this point is the Cm of the first rod. This point is the Cm of the second rod. So clearly we have xCm1 oops, XCM2, we have YCM1 and YCM2. These are the lengths we're interested in. Now, by some geometry, you can easily show that XCM2 is 3 times XCM1 and YCM1 is YCM2. Now, all we have to do is just differentiate these relations with respect to time. And you differentiate with respect to time twice, and you get relations for the accelerations as such. Now, for the left rod, as theta equals to 45, symmetry will just give you that the x and y accelerations has to be the same. This allows for the net acceleration to point this way. And the magnitude of A is given as such. And if we define the angular acceleration alpha, it's just A is just alpha L over 2, because this length here, because this length here is L over 2. So now that we have all the constraint equations out of the way, we can write our N2L. For the right rod, we can write something like that. So this is just an exercise for you to write it out, but we just consider all the forces. And for the left rod, we can take talks about the hinge, and for the right rod, we can take talks about the CM. So you can see here that we're just writing N2L and Euler's rotation equation. So this is just nothing fancy. The key part is how we managed to come up with this. And this all comes from the constraint equations that we have mentioned just now. So yeah, this example really was meant to show you how to come up with the constraint equations. After you have done all this work, it comes down to a matter of solving a whole bunch of simultaneous equations again. And you'll eventually get 7 over 10 mg after some hard work. So constraint equations are quite simple. You just have to deal with writing out coordinates, and it can be useful to define a coordinate system with some fixed point as the origin. Then you write down your x coordinates and y coordinates of points of interest, and then you just find some relation using geometry, and you differentiate with respect to time, either once or twice for velocity and acceleration respectively. And that's how you get your constraint equations. Okay, I'll check Discord again for any questions. Okay, no questions. Okay. In that case, we will move on to some of the problems in the problem set, because there were some requests. We will first do problem 2.14. Yeah, there was a request for this. Okay. Yeah, problem 2.14. Yeah. Okay. So here we have a rod of mass m and length L that is uniform. On a horizontal table, cm distance a from the perpendicular edge here. Rod is released from rest from a horizontal position, begins to rotate. Coefficient of friction is mu. So the physical situation is something like that, where I've labeled the forces and they are in play here. So again, go back to the same framework, right? Write Newton's second law, then write Euler's rotation equation. That's what you always want to do. And because here we're dealing with A and we're dealing with theta, it is perhaps more convenient for you to think about how you can write the equations in a way that is most convenient for your choice of coordinates. And I would recommend using polar coordinates for this question, because you're working with theta, so might as well just work with polar coordinates, right? So how we can do this is along the radial direction. So okay, we just take this point. This point is like our origin. So along the radial position, we have mg sine theta minus f equals to m a dot. Okay, the notation is a bit bad, but a is like your r in this case, minus theta dot square a. And you have, for your tangential direction, you have mg cosine theta minus n equals to m a theta dot dot plus 2 a dot theta dot. Now, the signs are quite important here. For the tangential direction, is actually for both cases, it's just easy to see that whatever increases a will be positive, whatever increases theta will be positive, basically. Okay, this can be simplified because this is a is constant, so these two terms will die out. So you just get mg sine theta minus f equals to minus m a theta dot square. Mg cosine theta minus n equals to m a theta dot dot. Yeah, okay, a is constant because slipping hasn't begun, so the rod is still moving like that. Okay, so now you have two things like that. What you want to do next is so now you have this. You can now write Euler's rotation equation. And about here, so about this point, your net torque will just be mg a cosine theta, and this is just I theta double dot, because this torque increases theta. This will be half ml square plus ma square theta dot dot, parallel axis theorem for this one. And now that we have this, this implies that theta dot dot equals to T(a) 1 over 12 L square plus A square cosine theta. And from here we have, from here also, okay, we can write this by invoking the special chain rule thing, and integrating both sides, you get so you have this. Yup, you have this. Okay, I'll just put the limits of integration. Okay, so this is your theta dot square. Okay, but cool, because you have another expression here that involves theta dot square. So this allows you to write f equals to mg sine theta plus ma 2ga 1 over 12 L square plus a square sine theta equals to mg sine theta. We can take out the mg sine theta. This will become 1 over 12 L square plus a square. The top will be 1 over 12 L square plus 3a square. Yeah, correct me if I'm wrong with the algebra, but yeah, it should be this. Okay. So that's your friction. That's your friction. Then your normal force here is just given by mg cosine G cosine theta minus ma theta double dot, but your theta double dot is given by this, which allows us to write MAGA cosine theta 1 over 12 L square plus A square. This should give you wait, should give you this. Let me just check. Yeah, this gives you, this should give you this for your n. And what's left is just putting in your non-state condition, which you can solve. And with these expressions here, a lot of things cancel out. So it's quite easy to solve for theta. For the other part is just a simple case of the first part where only a quarter of the rod's length is on the table. So if only a quarter of the rod's length is on the table, your L, so your A is just L over 4. And you can just plug that in here and you should get, I think if you plug that in here, you should get this. It's your final result. Yeah. Okay. Anyway, the point of this question is you start from this, you draw a diagram, you write Newton's second law and Euler's rotation equation. You realize that polar coordinates is a better choice of coordinates to work in because you are dealing with theta anyway. And you can just get a whole bunch of equations here that involve theta double dot and theta dot squared, and you can simplify them. And don't forget your non-state condition here. And that's how you solve this. That's how I solve this problem. Yeah, I hope that clarifies. Okay. If not, we have a bit more time to go into other problems. I want to go into this problem here. So here we have some sort of a rotational collision where this cylinder is rotating, then it collides with this step here. And after it collides with this step, you want to find the angular speed of the cylinder immediately after the collision. You want to find the minimum value of omega naught such that the cylinder is able to roll up the step. Okay. So the hint here is that if you have a very short collision time, some quantity is conserved. And I get you to explain why this quantity is conserved. So what exactly is this quantity that's conserved? Okay, so I think this is quite guessable, but if you're dealing with rotation, it will be angular momentum. And yes, indeed, angular momentum is conserved. But why? So you can first label forces on this cylinder. Mg. This will be N. Then if the point of then the point of contact doesn't slip. So yeah, that should be that'll be that. So you're given that the collision time is very short, and the only thing that you kind of know that relates to time, right, is this equation. The angular impulse momentum theorem. Now, the key point to note is that actually if you take torques about this point here, I'll just draw in blue, this point, the only torque that's kind of present is your mg, right? Because your n, the torque is zero about this point. So mg is present. But you have to remember that your mg is a finite force. It's finite. And it will never change. It will always be mg. Whereas your things like your n are non-constant. It can change. And it can just go as big as it wants, basically. But because you're dealing with a finite force, and you're dealing with a very small time, then this quantity is very, very small, right? Which is approximately zero. And you will just get your change in angular momentum is approximately actually zero because of how small your mg is over this very small period of time. So this is actually the trick. So to explain why angular momentum is conserved is because you're dealing with only a finite force of mg and the time is very small. So the angular impulse by this force is very small and almost zero, which means that your change in angular momentum is almost zero and your angular momentum is basically conserved. That is why you have this. So that explains the why. So now that you have the why out, you now know why the very short collision time is important. So now you have forces on the cylinder, right? So what you want to do next is to apply COAM because you have established that it's conserved. Now, where do you want to apply COAM about? So here we have R, big R. Now, easiest point to apply COAM about would definitely be this blue point here. We want to apply it about this axis. So COAM. The initial angular momentum would just be this. Because because there's no slipping initially. This is your initial angular momentum. Your final angular momentum, as it rotates about this point as it's going up, because you can see that when it's going up, it's like basically rotating about this point, right? It's doing something like that, where it's rotating about this point. So when it's going up, you can take the moment of inertia about that point, which will be I plus mr squared omega. So this is your COAM equation. And in this case, it's a cylinder. Your I is just this. So if you plug this in, you should get your initial. No, you should get this. And you can do some housekeeping here. Which you can eventually arrive to this. And that's your angular speed immediately after the collision. So this is part one. Now for part two, now after the collision already happened, then there's no more dissipation of energy because the collision was the only thing that was inelastic and that dissipated energy. Now you can use energy. So how to use energy? You remember that your rotational kinetic energy exists. So we write this. Oh wait, no, this should be. Yeah, so okay, remember that we are still taking this point as the rotation point. So your moment of inertia in this case is still I plus mr squared by the parallel axis theorem. So by energy, at the minimum, omega naught, your whole cylinder will just be at rest at the moment your cylinder successfully rolls up. So at the end, you only have GPE. So this is your COE equation. Now you can just plug this in. You should arrive at this. This can be simplified. Yeah, this can be simplified to this eventually. That's what you arrive at. Okay, so this is a matter of using COE. The perhaps more important part is the first part, where it allows you to rationalize why, even though you have a torque, technically in this case, because your torque by your mg is not, because your torque by your mg exists. But using some approximations, you can make sure that you can still apply conservation of angular momentum by rationalizing that, okay, we have a finite force acting over an infinitesimal time. That's why a finite small force acting over an infinitesimal time, which is why your angular momentum is conserved. So this explains why you're able to use COAM, even though you have a torque, technically. Okay. So that's for this problem. We have time to, I think, go through one more problem. I think we can. Let me just see if anyone has any requests. Okay, there are no requests. I think we can just go through 2.13. So here we have another rotational collision problem. We have two dumbbells with masses m at each of their ends with length 2L each. They're colliding like that. It's again an elastic collision, so energy is conserved. We want to find the angular velocity of the rods right after the collision, and we want to determine the subsequent evolution of the system. So what does this subsequent evolution mean? It kind of sounds weird, right? Like this kind of sounds weird, but you see later on that this actually has a nice meaning in the context of this problem. So the first thing is, just like all rotational collision problems, you write your three equations: COE, COM, COAM, and you solve your three equations. Again, you probably realize that COAM is the hardest one to write here, and I will try to explain why it's the hardest one. So okay, after your collision, your system kind of looks like that, as shown here, where your two dumbbells basically move away at some speed v1 and rotate at some angular velocity omega, as shown here. So we might first want to write COE because it looks approachable. So what does COE tell us? With COE, we can write 4 times half mv1 square plus half mv squared plus equals to 4 times half mv1 squared, because all four have the same translational velocity, and plus, this is plus 2 times half I omega squared. Okay, at this point, it might be useful to just find what I is. I is m 2L over 2 squared times 2, which is 2ml squared. Okay. So this will simplify to half mv squared equals to, the 2mv squared equals to 2mv1 squared plus 2ml squared omega squared. Now let's cancel the 2, cancel the m. So V square equals to V1 square plus L square omega square. This is what we got from COE. Okay, now we need to now we need to write COAM. So what can we write from COAM in this case? So COAM. Now, how do we apply COAM? For here, easiest way to actually apply it is to apply it through this axis. And okay, let's just see how we write the equation about the axis first. So about the axis, we can write uh 4mvl, that's the initial, equals to 4m L square omega minus 4m V1L. Right, that's your final. And negative here again because direction is important. You can verify the direction by yourself by taking your right hand grip rule and cross product. Okay, this simplifies to V1. Yeah, this simplifies to V1. Okay, cancel L as well. Okay, so V1 plus V equals to L omega. Okay, great. This actually gives you also V minus, no, V square minus V1 square equals to L square omega square. So now we can solve these, right? So we have this. Let's plug in this. And so after we plug in this, we have V minus V1 equals to L omega, but also V plus V1 equals to L omega, which implies that V1 actually equals to 0 and V equals to L omega. So omega equals to V over L. So okay, we found something quite interesting here. V1 equals to 0 and omega equals to V over L. So it means that actually these two rods stop right after collision. And they only rotate. So they just stop moving, but they only rotate because V1 equals to 0. So that's actually quite interesting. And now you can see that if they stop and only rotate, okay, by the way, that solves part one. Yeah, part one is V over L. So okay, let's look at part two. So actually your two rods are just doing this. So okay, this is right after they collided. So they're actually just rotating. Like that. So one is rotating like that. So they're actually just rotating like that. Which means that actually after they rotated a full circle, right? No, actually after they rotated by 180 degrees rotation, they will collide again. And basically what happens is that the reverse situation happens. So we end up looking like something like that. And the reverse situation happens. They collide again. This happens. And actually, you already solved the problem just now, right? Because the reverse situation happens. So what actually happens to the system is the rods just actually just move like that. Away from each other again. And this is what happens to the system after the first collision. And once they move away, they will never meet again because they're moving opposite directions. So actually, you can see that by using the reasoning of the first collision in reverse, the rods just lose their angular velocity. They regain their initial translational velocity, and it's basically as if the rods just pass right through each other, but flipped upside down. And that answers the second part of the question. So the rods will just flip upside down and move like that. And that is the subsequent evolution of the system. And yeah, that is how you solve this rotational collision problem. Actually, you didn't even need COM because it wasn't asking for. Because once you found out this, then your whole problem's already kind of solved. Yeah. So that's actually kind of neat in this case. In general, I would advise you to write these two first. Because it's like a confidence boost. They're easier to write. Yeah. Okay. I will check the chat for any last questions before we end today. Okay. If not, then since it's 6, I think we can call it a day. And yeah, thanks for coming for a lesson today. And you guys are free to go. Thank you.